Hello children, and welcome to my next video. In this video we will talk about the chemical properties and trends of group 16 elements. So let us start with oxidation state of group 16 elements. The elements of this group shows -2, +2, +4 and +6 oxidation states. +6 is the group oxidation state, but oxygen cannot show +6 and +4 oxidation state. Instead, oxygen shows -2 oxidation state in most of its compound. In peroxides, oxygen goes for -1 oxidation state even. The stability of -2 oxidation state decreases down the group. Polonium hardly shows -2 oxidation state in any of its compounds. Also, the stability of +6 oxidation state decreases down the group due to inert pair effect. In fact, the lower members of the group prefer to exhibit +4 oxidation state. +6 oxidation state is thus more stable in sulfur and least stable in polonium. The compounds that have group 16 element in +6 oxidation state shows only oxidizing property. For example, H2SO4 acts as a very good oxidizing agent because in H2SO4 sulfur is having +6 oxidation state. The reactivity towards hydrogen, that is formation of hydrides. The general formula of hydride of this group is H2E. E is the element of group 16 like oxygen, sulfur, selenium, tellurium, polonium. Generally, the hydrides of sulfur, selenium, tellurium are prepared by the action of acids on the metal sulfides, selenides or tellurides. For example, a very famous hydride of sulfur is H2S. It is prepared in Krebs apparatus, what we use in chemical laboratories, by the action of H2SO4 on FeS. The reaction goes on like this: H3O plus from H2SO4 FeS, and it will give H2S gas. All hydrides have angular shape involving sp3 hybridization of the central metal atom. The bond angles in these hydrides decreases down the group. Like H2O has bond angle 104.5 degrees. Gradually the bond angle decreases, and in tellurium the bond angle is 90 degree. The reason for this, due to stronger lone pair bond pair and lone pair repulsion, the bond angle in water decreases from the normal tetrahedral of 109.28 minutes to 104.5 degree. There is greater repulsion between lone pair. So due to this repulsion and lone pair repulsion and lone pair bond pair repulsion, what happens? The bond angle shrinks a little bit. So normally the tetrahedral bond angle is this 109 degrees 28 minutes, but in H2O we found it only 104.5 degree. Further, as we move down the group from oxygen to tellurium, the size of central metal goes on increasing and electronegativity goes on decreasing. As a result, what happens? The position of two bond pairs shifts away and the repulsion between bond pair decreases, and so the bond angle decreases as well. Thus, down the group, what we have seen, the bond angle decreases. The physical state of hydrides, if we talk about the physical state, color and odor, H2O is a colorless, odorless liquid, while the hydrides of all other elements have an unpleasant foul smell, like H2S has a smell of rotten egg-like. Boiling point of hydrides, H2O has exceptionally high boiling point due to strong intermolecular hydrogen bonding. Oxygen form another hydride, which is H2O2, hydrogen peroxide. The structure of hydrogen peroxide we have already studied. Other elements do not show hydrogen bonding. The boiling point as we move from H2S to H2TE increases regularly. H2O has highest boiling point due to intermolecular hydrogen bonding, but gradually as we move downwards, the boiling point increases regularly due to increase in van der Waals forces and increase in size of atom and molecular mass. So van der Waals force is directly proportional to molecular mass. So as the size of central metal element here increases, the van der Waals force also increases, and hence the boiling point goes on increasing. H2O has exceptionally high boiling point due to presence of intermolecular hydrogen bonding. If we talk about the acidic character of hydrides, hydrides of group 16 act as dibasic acid. This is clear from this equation. It first releases 1H plus, then again releases 1H plus. The acidic strength increases down the group. The reason is that the EH bond strength decreases. The size of E increases and EH bond strength decreases. The release of hydrogen becomes easy, and when the release of hydrogen becomes easy, the acidic character increases. The comparison can be seen with the help of these Ka values. We know higher the value of Ka, more stronger is the acid. So here for H2O, Ka value is 1 into 10 to the power minus 14, but for H2TE it is 2.3 into 10 to the power minus 3. Similarly, the thermal stability of the hydrides decreases down the group because of the EH bond strength only. The EH bond strength, since the EH bond strength decreases, so as soon as it is heated, the bond breaks, and this particular compound H2TE is least thermally stable because the bond between H2 and Te is very weak, but H2O is most stable. The reducing character of the hydrides also increases down the group because of this strength of EH bond. Except H2O, all other hydrides are reducing agents. In fact, the increase in the reducing character down the group is due to the fact that the strength of EH bond decreases, and as the strength of this EH bond decreases, it will break easily and H will release faster. If the H will release faster, it will act as a stronger reducing agent. So H2O, H2S, H2Se, and the most reducing is H2Te. If we talk about the reactivity towards oxygen formation and the formation of oxides, the group 16 elements form two kinds of oxides, that is EO2 and EO3 type, that is dioxides and trioxides. Here is a table in which we can see that sulfur form two types of oxide. Similarly, selenium also form two types of oxide. Tellurium forms TeO2 and TeO3, but polonium forms only a dioxide and no trioxide, because +6 oxidation state is very unstable for polonium due to inert pair effect. The dioxides, the general preparation of dioxide, like for sulfur, it can react with oxygen and give sulfur dioxide. Sulfur dioxide exists as a discrete molecule even in solid state. These molecules are held together by weak van der Waals forces of attraction, and therefore SO2 exists as a gas at room temperature. SO2 has a very discrete structure, and the molecules of SO2 are held together by weak van der Waals forces. So SO2 is a gas at room temperature. SeO2, which is the dioxide of selenium, is a crystalline solid. In gaseous state, it exists as a discrete molecule and its structure is similar to that of SO2. However, in solid state, the SeO2 is non-planar polymeric structure. TeO2 and PoO2, that is tellurium dioxide and polonium dioxide, are non-volatile crystalline ionic solids. TeO2 in solid state has a layered structure consisting of TeO4 units. SO2 is acidic in nature and it dissolves in water to form sulfurous acid H2SO3. Similarly, SeO2 also dissolves to give selenious acid H2SeO3, which can be isolated in crystalline state. Sulfurous acid cannot be isolated, but selenious acid H2SeO3 can be isolated in crystalline state. TeO2 is amphoteric POO2 is also amphoteric, but if we consider the basic character, POO2, that is polonium dioxide, is more basic than TeO2, because as we know, down the group metallic character increases, so polonium is more metallic with respect to tellurium. Hence polonium oxide is more basic than the tellurium dioxide. The acidic character of dioxides of group 16 elements decreases as we move from sulfur to polonium. Thus SO2 will be most acidic. If we talk about the reducing property of dioxides, the +6 oxidation state of sulfur is more stable than +4. For sulfur, +6 oxidation state is more stable. Hence, SO2 acts as reducing agent and it oxidizes itself to +6 oxidation state. Further, the stability of +6 oxidation state decreases from sulfur to tellurium. As we know, the +6 oxidation state, the stability of +6 oxidation state decreases down the group because of the inert pair effect. Therefore, reducing character of the dioxides also decreases, while the oxidizing character increases. These two are vice versa. If the reducing character decreases, certainly the oxidizing character will increase. TeO2 in fact acts as an oxidizing agent. If we talk about trioxide, the general formula of group 16 trioxide is EO3. Like O3 and SO3 are gases, sulfur in SO3 has sp2 hybridized. Here we can see the structure between of the sulfur, the bonds between sulfur and oxygen. There are 2 p-pi bonds and 1 p-pi-d-pi bond. There is 1 p-pi bond and 2 p-pi-d-pi bonds. So with this oxygen, sulfur forms p-pi bond, but with these two oxygens it forms p-pi-d-pi bonds. Sulfur is having d orbital, although oxygen doesn't have d orbital in its valence shell, but sulfur have, so p-pi-d-pi bond can be possible. Here the resonating canonical structures are there, so the bond is moving. Now this particular bond is having p-pi and these two p-pi-d-pi, and then again there is a movement. Now from here to here this bond will become p-pi and these two bonds will become p-pi-d-pi bonds. Due to this resonance, the bond length of sulfur oxygen, due to resonance, the bond length of the sulfur oxygen for all three bonds is equal. It is about 142 picometer and bond angle is about 120 degree. The molecule is trigonal planar in structure. The molecule of SO3 are held by weak van der Waals forces of attraction. Therefore, SO3 exists as a triangular planar gaseous molecule at room temperature. Due to its trigonal planar structure, the three SO bond dipoles cancel each other and the overall dipole moment of SO3 molecule is 0. If we go about the structure, in solid state, SO3 exists as a cyclic trimer. In solid state, SO3 exists as cyclic trimer. We can see here the structure. This is the cyclic trimer. Three molecules of SO3 are joining together, hence it is known as a trimer, and it is a structure of cyclic trimer. Or a linear polymeric chain. So this is the linear polymeric chain of SO3 molecule. It is a linear polymeric chain of SO3 molecule. This is the planar structure of SO3 molecule. SeO3, selenium trioxide, on other hand, exists as a cyclic tetramer. SC4O12 in solid. So this is the structure of cyclic tetramer of SeO3. There are 4 SeO3 molecules joined together and a tetramer is formed here. Solid TeO3 has a network structure. It must be noted that all trioxides are acidic in nature. Thus, the various properties of oxides and hydrides of group 16 elements are discussed in this video. I hope you have understood the things. Thank you, children.